just as I can make a position for the center of mass, I can also find the velocity of the center of mass. Because you guys know masses can move, so if the center of mass can have a position in space, it must also have a velocity in space. So a moving object's center of mass is also moving. So here I have the velocity of the center of mass, and all I've done is taken out the position and replaced it by the velocity. So we have 1 over capital M, that's the total mass of the system. We sum up each individual particle with their individual velocities. Now, I haven't done this in 3 dimensions, but obviously you would do this with a Vx, a Vy, and a Vz to find the x, y, and z components of the velocity of the center of mass. What's important to note here is that Newton's second law still holds for a system of particles. If you remember, Newton's second law is that force is equal to mass times acceleration. I haven't used the vector quantities here, I'm just keeping it in terms of magnitudes. Force is equal to mass times acceleration. Now what Newton's second law says for a system of particles is that the net force is equal to the total mass of the system, capital M, multiplied by the acceleration of the center of mass. So now we have that the net force being applied to a system of particles is equal to the total mass multiplied by the acceleration of the center of mass. And if you look up here, we know that the acceleration of the center of mass, all we do, the same way we did with the velocity of the center of mass, is take out this velocity right here and replace it by the individual accelerations for each particle. Okay? Now, F net is going to be the sum of the external forces. In order to change the velocity of the center of mass, I have to apply an external force. This does not violate anything that we've talked about previously when it comes to Newton's laws. Think about it. An object with a constant velocity means that it's not experiencing an acceleration, and if it's not experiencing an acceleration, that means that there is no net force acting on it, no external force. So that means that in order to change the velocity of the center of mass, we have to experience an acceleration of the center of mass, and that means that we must have a net force that is an external force. That is an external force that's being applied to the system of particles. Okay? And again, capital M stands for the total mass of the system. Okay. So now I've talked about external forces a lot. External versus internal forces. Okay? Now this is important. This is where people get a little confused. So I want to spend a little bit of time talking about external and internal forces. I'm going to reach off screen again. Now, the best example I can give for external versus internal forces is to think about the pool table down in the student center. Okay? Those pool balls will sit on that pool table from now until eternity because there's no external force acting on them. Okay? The pool balls are just going to sit there. When you come over with a pool cue and you strike one of the pool balls, you are an external force that's being applied to the system. You are coming from outside the system and you are going to interact with those pool balls. Okay? If I pick up one of those pool balls, see, athleticism right there. If I pick up one of those pool balls, I am applying an external force to the system. That means I'm giving the system a net force. That means I am changing the acceleration of the center of mass. Okay? Now where it gets confusing, when you strike the cue ball, and it goes and it now interacts with the other pool balls, the external agent was you striking the cue ball. Now that cue ball is moving, okay, and it is going to strike and interact with the other pool balls. These are all going to be internal forces. These internal forces will not change the velocity of the center of mass. Remember, this net force right here is an external force. These internal forces, these interactions between all of the pool balls, they're all going to shift and interact with each other. You guys see it all the time. Cue ball comes in, hits one of the other pool balls, they continue to fly off. But those internal forces, because they are interacting with each other, okay, Newton's third law, action-reaction, correct? Because those internal forces are happening, the velocity of the center of mass will not change. Because the only way it can change is if there is an external force. So you coming in and hitting the cue ball, you are the external force. You are disturbing the system of particles. Now those particles are going to interact with each other. Those interactions are all going to be internal interactions using internal forces, and that will not change the velocity of the center of mass. Now this is a trick that comes up sometimes on some of these AP problems. And by extension, it leads us into a conversation of momentum and the conservation of momentum, which is what we're going to go into right now.